Thank you, everyone. Thank you for coming today. So, as I mentioned before, we're talking about why we should standardize and what we can learn in the streaming space from what has happened in the data processing space with around Apache Iceberg. Right. So, in the data streaming space, there's lots of significant costs associated with the distribution of nodes across multiple AZs. Right. This is your traditional Kafka application, and this is the cost paid for high availability and data resilience. Right. You want to have data durability across Kafka because Kafka was built on the assumption that it's responsible for its own data storage, right? I own the data. I'm a system that sits on top of the data. Therefore, I'm responsible for its care and feeding and making sure it's available at all times. The impact of that is obviously a lot of different costs, and this data replication mechanism is one of them. Part of this downside of this data ownership model comes from the high infrastructure costs driven primarily with the data replication enters the AZ costs. Operational complexity is also related to this data rebalancing, right? Because your job as a broker to make this data available at all times. If you add another partition, you have to rebalance the data, broker availability, data going down, things like that. Some of these things, because you have this operational complexity and you have this feature compounding fact that ability to add additional features and evolve the system over time has slowed down. Because the system becomes very complex. So even very small changes, things that you can make very rapidly to a system like this and owns its own data, it has a lot of different, moving parts. You can't make the changes very quickly because you have to measure the impact of other systems and things like that. So sort of slowed down evolution of Kafka. We noticed that things have not come out as quickly as possible overall as a system. There's some kits sitting around and improvements have been sitting around for years. And it's just become it's sort of reduced the friction from an innovation perspective. But having said that, there are some things that have shifted away from those sort of things that we're moving for in the Kafka community. Around, we've seen it overall as in the ecosystem. The things moves towards, diskless architectures. That's a kit that become primarily exciting. As we talked to the previous talks, you've seen that people can now stream data into the lakehouse. That's a common, pattern. It allows you to use object storage instead of disk-based storage to reduce that data replication tax. You also have leaderless architectures that make things more, to reduce the operational burden. If a broker goes down, it's not the end of the world. And so the stream to lakehouse is becoming an emerging pattern, right? That reduces the time for the data. You're ingesting this data, becomes an ingestion pipeline. Everybody's built tools around Kafka. Kafka is a great way to move data from your source into your systems. But there's this like ETL pipelines built around this. So if you go directly to the lakehouse now, people, can, from the time the data's, produced, 30 seconds later, you can read the data. That's very, very efficient. People really like this. Last but not least, these storage formats allow, different, developers to escape some of the constraints of partition-based storage. We just had a conference yesterday, and OpenAI gave a talk around how they have ingest Kafka at scale. And I said, well, what we do is we just sort of, ignore the fact that it has partitions, we ignore ordering, and we just shove it into a pipe. And then the other side of people need it, we sort of work around that. So it's kind of a constraint that was there forever, and people found ways to get around it because it puts some constraints on the way you store data. So people are rethinking how you store this in these data formats. Right. So as developers of a Kafka compatible streaming platform, that's what we do at Stream Data. We're the founder, we do Apache Pulsar. We also do Apache Kafka compatible streaming engine. We were inspired by some of the benefits from the data processing community's adoption of Apache Iceberg as a standard format, right? It's kind of interesting to see once the community coalesced around this is the way we're going to store data, innovation really became, it spun up very quickly, right? Parquet and Iceberg have been around for a few years. I've been in the big data space for, before I came into the streaming space, and Parquet's been around for 8-9 years. Like, how can we get all exciting all of a sudden? Because people decided, like, hey, this is the way we're going to move forward. And once the community decided to accept this as a standard, people could start saying, okay, now we're safe. These open table formats give us the confidence that we're going to build on this ecosystem. We're not locked into a specific vendor. Our data is free and it's liberated. We store in a format. We put it in our object storage, and it's ours, and we can process it in different ways. And so you can build tools around that, knowing that the rule's not going to shift underneath your feet. And it's a really, really good way to do that. So we said, this is really great. There's a lot of different things that came from that. So we asked ourselves, why can't you benefit from that? If we can standardize the data processing world on something like Apache Iceberg, why can't we do it something similar for the stream-based community, right? We're all different Kafka vendors out there. We all have our different ways of storing information and stuff. And so we have to figure out how we store things differently, right? At the heart of every streaming platform lies the distributed log system, right? It's just really what Kafka is, or any sort of Kafka system is just a fancy covering on a distributed log. Right? So from a logical perspective, this is really just an unbounded depend-only data structure. However, obviously, to implement that logical, abstract data abstract, it requires a lot of different metadata on the covers to really store it at the physical layer, right? There's different ways of storing this information, right? There's a lot of metadata required to track where this data exists, right? And so you can have different parts of it sitting around in different segments. In Pulsar, we use a segment-based storage system. Actually, segment-based systems where in things like Kafka, they do these different things. They store it as a partition-based system, and the metadata is stored on the physical device with the broker itself. So you have information within that partition itself where it is. And so this introduces a bit of an operational burden. I was moderating a panel, and the CEO of Red Panda was there, and I asked him about what the time do you realize that latency? He says, there was one customer with his head like 5.4 gigabytes per second of data metadata that's come out of the brokers to serve it. Like there was so much metadata required process every time to move this data around that became an operational burden for that, right? It's a lot of overhead. The metadata becomes a serious concern at higher scales, right? And so obviously you want to move the data to object storage, right? Kafka, has been using object storage for years now. Pulsar has been using it as well. And really just involves serializing the bytes, these little bits and pieces, these metadata bits of what you have inside your topic data, moving it to some sort of object storage, and then updating your metadata, right? So this data doesn't exist on my local disk anymore. Now it sits out in object storage at this particular bucket or whatever it might be. And as you can see, as you update these things, you have to update the metadata inside each of the brokers as well to point to the new location, right? Apache Pulsar, the way we did it, we based it on a different way. We'll get to why. So I'm not here to trash different systems, but just say we took a different approach on how we do things. And our store layer is completely decoupled from the brokers entirely. So we have a true segment-based system. You create a segment, and have partitions, the concept of partitions for storage. And what we can really do is just have these the metadata, the offset index, and we keep inside our, used to use Zookeeper. Now we've eliminated Zookeeper as well. And we have something called Apache Oxia. Or it's not really it's not Apache, it's just Oxia. That we do it, it's our metadata store. We keep the offsets there. So that Oxia is already moves the data outside of the brokers entirely, outside of the storage layer entirely. And there's many advantages to this approach because you completely move the metadata away from the way the data is stored, right? Which is very similar to a pattern you see with the cataloging, right? We were starting to move towards the Iceberg adoption as you have these three different parts. You have the data itself, you have a catalog around what's in your data, and then you have an API way to access this sort of thing. And so by moving this data to an intermediate storage, it's a nice conduit. It's a natural way to offload that data into object storage, and you update the offset inside a metadata store rather than on each broker itself. And it makes it very easy to do. And so we looked at our design, and we think we made some improvements. You get Kafka, we're not digging to judge systems, but you can see that they follow a similar pattern, right? It's like databases. People develop databases, and they have certain core parts. Every database has these sorts of things. And we said, what are the three core components of a streaming system, right? It's the streaming data itself and where it sits. It's the data. It's the what. It's your topics. It's the metadata associated with where I've stored this data because I've had to distribute it all over, all these different locations, object storage, local storage, different, Iceberg formats, things like that. And then last but not least, the client protocol used to publish and consume the data, the how I consume this data, right? So everything is there. So we looked at it and said, okay, we got these three parts, and it creates a certain triangle that mirrors what you see with the data processing system as well. And so we thought to ourselves, what we really need is, streaming need an Iceberg mode. They need a mode where you coalesce around a different storage solution, and we come up with a standardized way of doing things to spin up innovation as well. So with that, I'll hand it over to my CEO, presented a paper on this, and let him get into the technical details. Thank you all. Yep.
Thank you, David. I think the way how we're looking into data streaming, essentially, I remember that I attended a meetup with Jason Reid, one of the co-creators of Apache Iceberg. The way how he described Iceberg, the bone of the iceberg essentially is you kind of, every vendors was kind of developing different warehouses, but every houses have a similar common component, and the way how Iceberg is coming out is that P on any, and then just moving each component into some of the standard. And we feel what's happening in the data streaming space is we have Kafka, we have Pulsar, we have like Red Panda and Upstream. There are so many different vendors and trying to do exactly the same thing, and those are not interchangeable. And the only way for people to moving data around is moving data from like reading from one vendor broker to another vendor broker. Every replication is going through networking, and but that is very expensive. So once you log into a system, if you want to moving in out, you have to replicate the data out. So we feel we're kind of in a trap. That trap essentially is locking into one protocol, which is like very similar to what's happening in data warehouse before. Is you lock into a data warehouse vendor, you cannot be moving data out. If you want to moving data out, then you have to kind of go through these expensive database migration. So you're kind of looking back into what like maybe David was kind of talking about is that every data streaming system at the end of the day is kind of working on three pieces. One is your data, essentially how you store the data. The second piece is metadata, whether you are using an external like the Zookeeper auction or maybe some of the built-in route implementation. Those are still metadata. Essentially is a pointer to some of the data storing either in local disk or in a remote storage. So it's metadata. Using a fancy word that everyone know today in Iceberg is catalog. Catalog essentially is a piece of information pointing you where to read the data. And the last piece is basically the protocol, is how you access the data that is storing somewhere and using metadata and data. So we're looking into this. We're kind of in a situation. Why not we just looking into standardized data and metadata? So then you sort of having. Actually, sorry, I need to go back. So if you're trying to kind of standardize on some sort of standard, and that standard will give you benefits is the cost efficiency. So you just store one copy of data, and if there's any improvements in terms of the performance, you can do that in vendor specific engine, which is broker perspective. But you just need to store one copy of data. If you want to switch vendors, you can just switch engines, but you don't need to move your data because that is expensive. And secondly is decouple things into different pieces of standard would give people a faster evolution. So you can standardize on certain storage format, optimize for writes, optimize for reads. You can optimize for different workload patterns, standardize on certain like metadata access. So you can also evolve the metadata much faster. And then this would also enable what we call multi-protocol, is that because you just store one copy of data and each broker might be able to evolve much quicker to adding different capability on top of the same set of data. And obviously this will also give you reliability and much simpler operability there. So, but obviously protocol itself is just the API. A lot of our application is already building on Kafka. Some of the application might be building on Pulsar, on the other protocols there. So what we're looking here is more, probably you should not try to standardize on everything, is because if you try to standardize everything, getting into more like old JMS API world, is that I give you a JMS API, you implement JMS API, and you don't need to care about this JMS API, but it doesn't serve the purpose of helping everyone. It's just every JMS vendor is trying to log you into the same silo there, because you cannot move data around. So our idea is that what Iceberg is doing is to creating some of the storage standard. Why not create same like streaming storage standard for all the like data streaming vendors, and that should be just focused on data and metadata. So that's kind of our vision, and then we taking our vision into kind of implementing one of the system is what we call URSA. It's a reference implementation. You can just take it this as a lessons that is we as a vendor, as a kind of a someone working in the data streaming space for multiple years, we have a vision. We have the hope to pushing this industry towards more like open standard, similarly with what's happening in the Iceberg side. And more importantly, I think Conference give a pretty good talk about like table flow. Getting data from Kafka to Iceberg is very common. And at the same time, we also want to making sure we are leveraging existing open standard that Iceberg is already kind of creating, that we can reuse it and build a broader kind of a standard on top of an existing open standard. And that's kind of what we take to build a system called URSA. And I'm not going into every details there. We recently published a paper, submit a paper to VODB 2025. And that paper was also selected as a best industry paper. There's a QR code. If you scan the QR code, it will go to the VODB website. I'm not going to the Stream Native website, so it's not vendor content there. You can read more details about the kind of the tech, the URSA paper there. But I just want to give you a very high level idea in terms of how we think in terms of a streaming standard can be built out. So we just at high level is if you think about URSA is Lakehouse native data streaming engine, implement like Kafka compatibility, but underneath is it just implement the storage layer on top of like a pluggable storage engine. Majority focus on object storage, but if you want low latency, you can opt in disk-based implementation. But all the data eventually will be landed into object storage or lakehouse as the Iceberg table or Delta table. So that's kind of the architecture that we're presenting as the URSA as part of URSA. And if you kind of want to tie back into the conversation that David just talking about, is essentially when looking into data streaming system, there are only three pieces. One is the data, where you store the data, and how you reference the data, which is the metadata, and then you have the broker, which is serving the protocol, and essentially that the entire URSA system is built in this way. The most interesting pieces that URSA contribute to the entire industry or ecosystem is essentially that how we think about the streaming format can be standardized. And obviously, once you're getting into schema, once you're getting into tabular data, you're always looking into Apache. Apache is the standard for the entire lakehouse. So the way how we think about streaming is should also standardize on the same format. So in that way, once data land in stream, it could be immediately used as a tabular data. So that's kind of how we think about building about the storage format for streaming. However, the difference of streaming is different from tabular data or table. Is the streaming require fast ingestion and low latency tailing reads. So it's more looking into like a pen-only log. And with this pen-only log, you might be receiving writes coming from different topics. Like if, for example, in IoT, you might have millions of devices sending data, and each devices might be representing a topic. So you'll be receiving tons of data coming in. So in order to avoid, in order to get low latency, but at the same time, you don't want to get into a situation that you have a smaller file problem. So when we design the stream storage format, we introduce a concept called write-ahead log objects. So it's a way to aggregate the records coming out from different topics. So in that way, data can do low latency, fast ingestion, and you can also avoid the small file problems and reduce the ingestion cost. But in the background, we can have a background worker to keep compacting the write-ahead log object into more like per topic, columnar format using Apache file. So once this concept laying down, then the streaming format will become easier. The lakehouse table essentially is a bunch of the lakehouse Apache files with snapshot, checkpoint, then reference that. So once we have the Apache file, we can just assemble those Apache files as the lakehouse tables, and people can access those lakehouse Apache file via lakehouse table format. In order to supporting streaming, we can just lay down an index, what we call streaming offset index, and that index essentially is just to making sure we are able to reference the records coming into either red hat log or compact object. So you are able to read the data in the streaming orders, making sure order is guaranteed. So that's the entire concept of streaming format. It's built on open standard, building on Packet file. It have a really natural way to integrate with other lakehouse concept like Iceberg and Delta. So in that way, you can ingest once and be able to present data either as a lakehouse table or a stream. So once you have that, that's a little bit more details how we kind of organize the offset, like stream offset index is more likely using that stream offset index to reference where the data is stored, whether it's in Red Hat log object or in the Packet object, to making sure during compaction, you are always able to find the right same copy of the data, identical data. So we're not hitting this inconsistent issue there. And so once you have this foundation, then a lot of implementation, this is just a reference, again, is if you want to implement Kafka compatibility, you can just like call in this stream standard, pen the data, and commit the return like object into the index. So in that way, everyone can just mean the same thing because the underlying data is indexed and stored in a standard way. And similarly, then you can have a consistent way of reading data outside of the same set of data. So in this way, if every streaming vendors implement similar like follow form like a storage standard, in that way, you can just use the same way how you manage like Iceberg, managing the streaming data, and the broker will become just a caching layer, your batching layer. In that way, every vendors can just like optimize what they're good at, and all your data will just store one copy in your data lake as a streaming format. It could also be read as a lakehouse tables, and that's kind of the way how we think like the entire ecosystem in community are coming a long way to standardize Packet as a file format, Iceberg as a table format, and we should do something for streaming. And that's what there's a kind of a contributor in the data streaming community ecosystem for a long time. We can calling out all the peers in this space that we can work together to coming up with some of these stream storage standard. And that's all the talks. And for more details, I think you can still scan the QR code. You can read the paper in details. Obviously, have 2 minutes for questions.